I did want to comment, I put a solution set up for the homework. I'm really not, there's so many things to do, and you have to do all of them, and then you mess up. I probably have your homework back, but I forgot to look for it in the office, so I'll get it for you on Friday. It was a big assignment. I have to do them too, right, when I do the solutions. That was a really big assignment. It was a little bigger than I thought it would be. And, you know, it always can't hurt to work hard. But I just wanted to say, normally I try and have something a little, not quite as much. We were talking about rational functions on Monday, and I still have a few more things to finish up. The first is kind of something to notice. We have a function like this. Well, one way we can figure out what this function is about, graph it. We could go through the process that we've been going through. We can see right away there's a horizontal asymptote here, and we can kind of see the end behavior is going to go to 2. But sometimes there's another way to look at a function like this. Before I show you this, I just want to remind you about a very basic function we looked at, which was 1 over x. It's a hyperbola with the axis along y equals x. It has asymptotes along the x and y axis. And why I bring that up will make sense in just a second. The idea here is, though, that we can change the way this looks a little. We can manipulate it a little. I'm going to divide here. Use long division. And I get 2, so I get 2x plus 2, remainder 1. It's 1 over x plus 1. So I can rewrite this function as f of x equals 1 over x plus 1 plus 2. Okay, so what was the purpose of that? The purpose was, if you look at this, it kind of looks a little bit like our 1 over x function. How does it differ? Well, it's translated, right? The plus 2, that's going to translate it up, right? And then here, I've added 1 to x. Which way is that going to move the function in the x direction? To the left or to the right? To the left, right. So we know that if I just take this function and move it up 2 and over 1, then I'll have this function. I'm going to be lazy. I'm not going to draw it up there. I'm just going to show you. So this is what it would look like. The dotted line is 1 over x. And as you can see, it's just a translation of 1 over x. So sometimes when you have a rational function, you can use this feature we've worked on before, we've looked at before, which is translations. And you could simplify figuring out what you're dealing with. Okay, that was one little nit. I think before we go on, it's not an easy subject, and we're not spending a lot of time on it, but I think it's probably worthwhile to go over one more example before we move on. The example I want to use is f of x equals, and here's my p of x, 2x squared plus 7x minus 4. And my x squared, it's my q of x squared plus x minus 2. I just want to go through this problem from start to finish, see what we can find out. And I want to do it in a methodical manner. I want to first collect all the data we're going to need to do this, to graph this function, and then we'll move on. So let's start with the vertical asymptotes. All right. How am I going to find the horizontal, vertical asymptotes in this function? What am I going to look for?
Factors.
Okay. Which factors?
X squared plus x minus 2.
Yeah. Okay. So let's factor the denominator. The denominator. Okay, that looks pretty easy. That's got to be minus 1 and plus 2. While we're at it, let's try the upper function too. That may come in handy. 2x, x. Well, it's either 2 and 2 or 4 and 1. But if it's 2 and 2, I'm just going to get even numbers, and that's an odd number. So probably 4, okay. 8 minus 1, right? Okay. All right, so now I factored it. What does that tell me about the vertical asymptotes? Where are they? Don't everybody speak up at the same time.
And 1 and minus 2.
1 and minus 2. So x equals 1 and x equals minus 2. Okay, recall that the denominator is 0, you're going to get a vertical asymptote. Okay, that's good. How about the zeros? Where is this function going to be 0? Watch that, Richard. If you go like that, it looks like you're raising your hand. Richard, do you know where the zeros are?
I do not.
Okay. Remember, if we have a function, a rational function, p of x over q of x, where are we looking for the zeros? How do we find the zeros? Well, zeros in the denominator don't. That's not going to cross the x-axis. But we do want to look at p of x, right? It's 2x minus 1, x plus 4. Where is that 0?
Plus 1/2.
Plus 1/2.
And minus 1.
I missed this. What was the second thing you said?
-4.
Minus 4. Okay. Okay. How about the y-intercept? Where do I find the y? We're going to cross the y-axis. Where am I going to find that? Yes? Okay, it is 2, but why don't you tell everyone how you found that?
Because x is always 0 when you look for the y-intercept, so you just input 0 and not the x's.
Yeah, you plug in, the y-intercept is where f of 0 is, so all the x's drop out, minus 4 over minus 2 is 2. Okay, good. What else do we want to think about? We want to think about the end behavior. We want to think about what happens to this function as we get very large or very negatively large. Okay, how do we do that? Well, when x gets very large, x squared is going to dominate here, and x squared is going to dominate here. So really, we want to know, what does 2x squared over x squared look like? Looks like 2, doesn't it? So what does that tell us? If the end behavior of the function is 2 on both sides, what do we then have? Okay, remember there were 3 possible things that you have for end behavior. But you have an x down in the denominator. As x gets large, it's going to go to 0, right? You have an x in the numerator. Like if you had, say, x to the 5th over x squared, that would be x cubed. That tells you as you get far away, the function looks like x cubed. Right? So, we might not know what goes on in the middle, but we would know what goes on either end. This is different. This is, here we have 2x squared over x squared. These are the dominating factors when we get very large, it becomes 2. So what happens to our rational function? Anybody remembers? Yes?
That there's like a horizontal asymptote that it's approaching?
Yeah, there's going to be a horizontal asymptote. I'm not going to try and spell it. at y equals 2. Okay, so we have a lot of information. We don't have everything we need yet, but we can at least get started. So put up axis. Put a scale on here. And what do we know? We know we have an asymptote at 1. Vertical. We know we have an asymptote at -2. We have a horizontal asymptote at 2. Okay. And we have some points. We know we have a 0 at -4. It's over here. And we have a 0 at 1/2. It's here. And we have a y-intercept at 2. Okay. We also know that, you know, at these vertical asymptotes, the function is going to be discontinuous, right? It doesn't have a value there. Okay, well, let's start with this horizontal asymptote. We'd like to know where the function is coming at it from, right? It's either coming from above 2 or below 2. So let's pick a large number. Let's pick, you know, x very large. Let's say 10, right? So f of 10, that's out here somewhere. That would be 2, 10 squared, 200 plus 70 minus 4 over 100 plus 10 minus 2. That's 266, right? And 108. Okay. Well, that's greater than 2, isn't it? So that tells me it's coming down to this function from above. On the other hand, if I'm out here very negatively, let's try -10, see what that gives us. Again, 200. Now minus 70 minus 4 over 100 minus 10 minus 2. Say that's 130 minus 4 is 126. It's 90 minus 2, 88. Well, that's less than 2. So that tells me out here the function is going to 2, but from below. And we can see that's probably going to cross the axis at our 0 minus 4. Now we'd like to know what happens at these asymptotes. We could plug in a number on either side, right? We could plug in a number a little smaller than -2. So we could say, what happens at -3? So that's 18 minus 21 minus 4 over 9 minus 3 minus 2. Okay, so that's -7 over 4. About, -2. But what do we see here? It's negative. So just as it kind of looks, this it's approaching this asymptote, negatively. We could repeat that exercise, but you probably can see that it's coming up on this asymptote that way. And again, we can look on either side here, but these 2 points here can give you a hint that it's going to come down here. And it's going to go up this way. Again, you can always plot some points to get an idea. Okay, so that's our function. That's the graph of our function. Let's take a look. See what our graphing program tells us. much that's it. We have the vertical asymptote at 1, another one at -2, and of course the horizontal asymptote at 2. So, that's how one would go about evaluating, looking at these rational functions. Any questions about this one? Okay. Yes?
How come the two outer lines don't cross the horizontal asymptote, but the one in the middle does?
These don't cross the horizontal asymptote.
Exactly, but the one in the middle does.
Yeah. Well, in principle, they could, right? There's nothing we've done that says it couldn't do this, right? But on top, we just have a quadratic. And if it was like a 5th degree or 6th degree, you might expect more bumps in it. I'm just trying to think what. You ask a good question though, and I want to give you a better answer. Well, we discovered that it's less than when we plugged in -10. We found that it's below 2, right? How can we kind of convince ourselves that it, and we know here it's 0, right? So between here and far out, we know it's all beneath 2, but how do we know it doesn't kind of just jump up that way? Well, I think I have an answer for you, which is, right now we see that as it gets very negative, it's going to go to 2, right? That's clear. But let's look at the next term, right? This term here is greater than this term. Well, we're dealing with a negative number, so it's less, right? So, as we start to move out, this is dominating, and it's keeping us down below the line. I think if we switch this around, this is a guess. We're gonna experiment here, right? Let's see what happens. Well, we lost our horizontal asymptote. Why is that? Well, actually, out here it still is. Oh, I think I know what's going on. Oh, there it is. So now you see it's coming from above, right? So it didn't really do what I wanted it to, right? We lost our 0 right over here. I was trying to get it to come up by doing this, and now it just kind of goes off like that. So, and interestingly, it reverses on the other side. Yeah, I don't have a better answer, but I think you could look at this coefficient and you could tell right away that since this is greater, and since we're going negatively, it's not going to be above there. Well, good question. Wish I had a better answer. Somewhere in the book on polynomials, they start to talk about you know, like you look at something like this, you know, x cubed plus ax squared plus bx plus c, and you know, start to play around with the a and the b and the c, and you see what that does. You don't have to play with the c. We know what that does. It's just going to move the whole function up and down. But you know, a third degree could look like this, or it could look like this, right? And you know, there is some science to how does the a and the b affect these bumps. But when you need to know it, right, in your marine ocean biology class, you will come back and you'll get out a grapher and you'll figure it out. So. Okay, any other questions about rational functions? All right. We're now moving on to chapter 4 in the book, which discusses exponential functions and log functions. And we're going to learn all about them today. We're going to learn about exponential functions. So, before we do, I have a kind of a fun problem here that we're going to think about for a minute. It goes like this. In the future, you are interviewing at a super corporation called Apple, Google, Facebook. In the future, they've all merged. They are the best place in the world to work. You really want to work there. They have the best benefits and the highest salaries. And you've been interviewed, and you know they looked you over and they like you, but now they've given you the final test. They say, well, we'll need to pay you a salary, and we're giving you a chance to choose how you're going to get your salary. You have to make the right choice. If you don't make the right choice, you're not going to get hired. So, choice 1 is, your first day, you make 1 cent. And on the next day, you make 2 cents and then 4 cents. And it goes that way for the first month, for the first 30 days. And at the end of 30 days, that's your final salary. You'll get that monthly. No, you'll get that daily. Yeah, that's great. Yeah, daily. Okay, that's choice number 1. Choice number 2, you just settle for $100,000 a day. That sounds pretty good too, doesn't it? Before you get too excited, Starbucks coffees are now $50,000. You know, it's not as much as you thought. Okay, so you're guaranteed to be employed at this corporation for at least a month. And you have to decide which of the 2 choices you're going to make. And you have to decide now. So if you would like choice 1, raise your hand. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Who would like choice 2? That's supposed to be everybody else. Nobody, you don't want 100,000 a day? Sounds good. All right. Who just doesn't even want a job with Apple, Google, Facebook? All right. Well, let's figure this out. All right. We're going to get 1 cent and then 2 cents and We're going to have to add these all up. But what do we get on the last day? We get 2 to the 30th cents, right? Here it's easy. We make $3 million for the month. Right. Someone have a calculator? You want to tell me what 2 to the 30th is? Remember, that's just what we're going to make on the last day, right?
Yeah, it's ginormous. I can read it out to you.
Okay.
107, 37,
107.
37,
Mm-hmm.
41,
Mm-hmm.
82, 4.
4. Okay, so that's 24 cents, right? And, oh my gosh, on the last day and thereafter, you're going to make $10 million, 11 million almost. You know, you'll make about 5 million the day before and 2.5 the day before. That sounds a lot better than 3 million, doesn't it? Okay. The reason this is, for those of you who were surprised, the reason this is surprising, this is an exponential function. Exponential functions are kind of surprising. They actually show up, as we'll see in nature. But as you can tell, they pretty quickly an exponential function can get out of hand. There's a legend about the game of chess. I think it's believed that chess was invented in India, and there's a legend that the king had somebody come up with an interesting game, and he came up with chess. And the king said, "How would you like to be rewarded?" And the guy said, "Okay, just put a grain of rice on the first, square of the board, and then 2, and then 4, and continue on, and just give me the rice, and we'll call it even." And the king went to his accountants and said, "Okay, figure out how much rice," and he found out that all the rice in the world would not. So he killed him. He had the guy killed. That's what kings do when they have problems, That's the legend. Okay. All right. What is an exponential function? An exponential function is a function in the form a to the x, where a is greater than 0, and also a is not equal to 1. You could have a function f of x equal 1 to the x, but that would not be a very interesting function. It's just a constant function f of x equal 1. So, but if a is greater than 1, then we have an increasing exponential function. What's an increasing function? Anyone recall what an increasing function is? Need to know that. We have a kind of a feeling it goes up, right? Increasing function is a function where you have a and b. If a is greater than b, then f of a is greater than f of b. That's an increasing function. So as our x's get greater, our y's have to get greater. A decreasing function would be the opposite, right? If a is greater than b, then f of a would be less than f of b. If instead a is less than 1, so it's between 0 and 1, then we have a decreasing exponential function. Okay, we'll look at some of these in a minute. Here's something really neat about an increasing exponential function. If you compare some, we'll call it p of x, with some p of x function, the exponential function is not always greater than, but as you get out into large x, it will always dominate. It will always be greater. That doesn't sound so interesting until you look at, what if e of x was 1.00001 to the x. That's an increasing exponential function. Increases very slowly, right? I mean, if you plug in like 1,000, you're still less than 2 here. And I compare that with some p of x equal to, say, x to the 1 million. How about that? Make it a billion. Eventually, I can tell you, there's a point, there's some c, where if x is greater than c, e of x will be greater than p of x. From then on. So exponential functions are relentless. They're bigger than any polynomial function you can come up with. Or they get there. Okay, let's go look at an exponential function. Let's look at the penny function we were looking at before. Here we go. This is the function 2 to the x. You'll notice at 0, it's 1, right? That's its y-intercept. To the right, it's relentlessly increasing. But as you go to the left, the x-axis is an asymptote. It gets closer and closer to 0. It gets exponentially close to 0, which is to say, if you compared it with some polynomial that was also getting close to 0 in that manner, the exponential function would beat it out. It would get closer and closer much faster eventually. So, okay. Something else I wanted to say. All right. Exponential functions, all kind of increasing exponential functions like this, all kind of look the same. They have kind of the same shape, except for a dilation. I'll show you what I mean by that. Here I'm comparing f of x equals 2 to the x, and g of x equals 4 to the x. Well, if you think about g of x for a second, 4 to the x, that's really 2 squared to the x, which is really 2 to the 2x, which is just a transformation, right? In the y direction, it's just a stretch transformation. And if you look at this diagram of both of these functions, you can kind of see that. 4 to the x gets closer to 0 quicker, and it gets larger faster. Another thing we might look at is what happens if I try and transform f of x by multiplying it by some constant. So let me multiply 2 to the x by 8. Well, let's look at that for a second. That's really 2 cubed times 2 to the x, which is just 2 to the x plus 3. That is to say, multiplying an exponential function, trying to stretch it, well, sure, you're stretching it, but you're really not changing the shape of that function. You're really just doing a shift on it. Which way am when I change x to x plus 3, which way am I shifting it? Again, to the left or to the right? Did I do that right? For you? To your left, to your right? Which way does that shift it? Should be at the tip of your tongue. Let's see here. Whoop. It's a shift to the left. Right? Multiply this exponential function by any number greater than 1, it's just moving it to the left. And if I multiply it by a number less than 1 and greater than 0, it would shift it to the right. It's kind of like no one exponential function, know them all, right? All kind of the same in that way. I mentioned you could have a decreasing exponential function, or it would be between 0 and 1. So that would be like a of x, where a is less than 1. But if a is between 0 and 1, 1 over a is going to be greater than 1. So if I call that b, then this is just f of 1 over b to the x, where b is greater than 1. That's really b to the minus x. In other words, going from f of x equals a of x to f of x b to the x, we're just changing the x to a minus. And what does that do when you just change the x value to a minus? What kind of transformation is that? It's a reflection. Remember, that's a reflection in the y-axis. Let's take a look. Okay, so that's my penny function, only translated, reflected, as 2 to the minus x. It's just like, let me jump back here. Looks just like this function, only we've switched the direction of the x-axis. And of course, we were talking about these transformations. There's one more thing you could do. You could multiply the function by minus 1, and that would just turn it upside down, reflect it over the y-axis. Okay, so some new things about exponential functions. Okay, I'd like to do a real-world problem things are really useful. Anyone here know anything about nuclear decay? You have, you keep in your refrigerator some plutonium-235 or something, and it's decaying, right, all the time. Well, I don't keep anything in my refrigerator, though. You have something radioactive, and what does it have? It has a half-life. Also an exciting 3D shooter game, but nuclear decay has half-life. So what's the half-life? What does that mean?
How frequently the radioactivity decreases.
How frequently the radioactivity decreases by half. Okay. So if you have like a half-life of 1 day, and you on day 1 you have a pound of nuclear material. On day 2 you have half a pound, and then on day 3 you have not 0, now it's a quarter of a pound. And on the next day, an eighth of a pound. The thing you wonder about is, like, the first half of it decays, right? It knows it's supposed to decay the first day. How does the second half know that it's not supposed to all decay? The magic of nuclear decay. All right. So, okay, why am I talking about nuclear decay? Does anyone here have a cat? Cat people? Yeah, okay. Anyone have an old cat? Sometimes when cats get old, we're going to go off into biology for a second. We're going to come back to math. They get this condition in their thyroid. They get a tumor, not a cancerous tumor, but a tumor. And their thyroid grows, and they start producing too much thyroid hormone, and they're not hungry, and they lose weight, and it's sad. They waste away. People have this too. There are a few diseases of the thyroid. I think there's something called Graves' disease. Anyway, and interestingly, the treatment is the same. There is a really good treatment. What they do is they inject iodine into the blood, iodine 131, which is a radioactive isotope of iodine. Now, why do they do that? This is very clever. Turns out your thyroid needs iodine. In fact, everybody gets iodine every day. Does anyone know how you get iodine every day?
Tap water and toothpaste.
I don't. That's fluoride, but for the toothpaste. I don't know about the water. I don't think so. You get it in salt. Not that it's in salt, but if you look on your big tub of salt at home, it'll say iodized, right? Because they put iodine in it. Centuries ago, people would not have iodine, and their gland would get kind of big. It was called a goiter. But enough with the biology and human anatomy. So they inject the cat with radioactive iodine. I don't know, what was I talking about? Thyroid. The thyroid collects all the iodine, but it's radioactive. So it's up there decaying, and it's killing off the tumor. And they know exactly how much to put in the cat to kill just enough of the tumor to make the cat normal again. It's amazing. Okay, none of this would be important. Well, you already see radioactive, half-life, exponential decay. None of this would be important, except that even after, you take the cat down, they keep the cat for about 3 or 4 days, and then they give the cat back to you. They say, don't get too close for the first few days. Yeah, try that. Try not to get close to your cat. But the cat still has radioactive iodine in it, and it excretes it in the kitty litter, pees it out, and you can't throw the kitty litter into the garbage anymore because it's radioactive. So, like, what are you going to do? Well, I came up with this idea. I'm just going to store it. I'm going to store it. I'm going to figure out how long it's going to take to decay, and I'm going to store it. Say, okay. And I decided that whatever they gave to the cat, whenever it's down to about 1/1,000th the amount of radioactivity, I'll throw it out. Right? So I'm going to store the kitty litter in my backyard. This is real. This happened. Well, okay. Well, first thing, what's the half-life of iodine? Any of you here with a computer can Google half-life iodine 131, and you'll find out it's 8.02 days. Okay. That's pretty good. Let me make that into an equation, right? So the amount of iodine I'll have after so many days will depend on how much I start with. And then it'll be 2 to the minus half-lives. What's a half-life? It's the number of days divided by 8.02. Except I don't really know how much iodine is in the cat. I just want to know, I want it to decrease to that. So I want to know I of D over I of 0. Just 2 to the minus D over 8.02. Okay. Now, I want that to equal 1 over 1,000,000. So I can throw it out in the garbage. All right. We're doing exponential functions today. On Friday, we'll hopefully get to log functions, and we'll know how to solve this real easily. But since we don't know how to do that yet, we use kind of trial and error, right? So, created a little table here. That's how I worked it out. And, I tied my log hand behind my back, so we don't know how to do that yet. So here we have number of days, and here we have this ratio, current amount divided by original amount. So if I plug in for days 10, I get 0.42. Okay, that makes sense. Like 8 days would be half, so a little bit more, 0.42. And I go, okay, how about let's try 100 days. So again, if you plug this in here, you'll find that's 0.00018 days. I mean, 0.018% at that point. All right, you might be tempted to go to 1,000. Remember, exponential functions, they're very rapid. That would be too far. I'm just going to go to 150. And that gets us down to 0.00023. Well, that's close because 1 here would be 1,000,000th. So I just need to go a little further. Go to 160 days, 0.00001. Okay, so now I'm at 1,000,000th. All right? Took me 160 days. How many months is it? It's almost 5 months. Big barrel of cat litter sitting out the backyard. And then I threw it all away in the garbage. Okay. So that's an application of an exponential function. You too might find yourself in a position where you have an elderly cat and you have to store their cat litter, used cat litter. Okay. Some some more interesting things about exponential functions. Where are we here? Okay. If you have an exponential function, you recall something called the average rate of change. Average rate of change. Does anyone recall what that is for a function? If I have like an interval, A, B on an interval, what the average rate of change is? Marco?
Was it B minus A over A, or B minus A?
Yes. If you take an exponential function and you take points that are close together on the function, the average rate of change, if this weren't a curve, if these were straight lines, that would be the slope. And it turns out there's something really neat about exponential functions. You take the average rate of change at these points, and you graph them. Something I've fortunately done already. Okay, so there's my graph. I take these points, I find the average rate of change, and I graph them. And then I draw a line through them. And I find that I have another exponential function. Ooh, that's kind of eerie. Neat. It won't be the same exponential function necessarily. We'll see more about that later. But this would work for a decreasing function, so this will work for any exponential function. If you find the average rate of change along it, you graph it, you get another exponential function. So that's another neat thing about exponential functions. Last thing I want to talk about has to do with something that might not occur to you, might have occurred to you, might even trouble you and keep you up at night worrying about it. We've defined a function, as some value to the x. And there's a question about evaluating this. I mean, you have a calculator, you don't really know how that works, but you'd like to have some idea at some point. But I guess we want to say 2 to the x. If x is 1, well, we know how to do that. That's 2, it's 2, 4, and so forth. We've learned, using our laws of exponents and radicals, we've learned how to deal with fractions too. So if I wanted to raise 2 to the 123rd over 454th, I know how to do that. That's going to be 2 to the 123rd. I know how to do that. And then I have to find the 454th root. Well, that'll be hard, but at least I know what's happening. The question is, what if I don't have a rational number? What if I had, like, the square root of 3? What does that mean? What does the square root of 3 mean? I know some of you just sleep fine not knowing the answer. But for those who stay up, lose sleep, fail their exams, they feel compelled to give an explanation. Well, let's take square root of 3 and let's approximate it to to 1 decimal. And now let's look at, this is less than square root of 3. So let's look at 2 to the 1.7, which is less than 2 to the x. And then we're going to look at 2 to the 1.8, which will be greater than 2 to the x. Remember, it's an increasing function, so if I take points on either side of my point, I know they'll be less than or greater than. So this has a value of 3.2490, and this has a value of 3.4822. So I know this 2 to the square root of 3 is between these numbers. Okay. Let me use a slightly more accurate number. Better approximation for square root of 3. Now I get 3.3173, 3.3402. So this got larger and this got smaller, and 2 to the square root of 3 is still between them. Right? I could keep going. If I get down, when I get down to 1.73205 is my approximation for square root of 3. I get 3.32220. And here I get 3.3220. Well, I don't know what those other digits are. But I do know this one is greater, this one is less. So what I'm doing is I'm kind of squeezing the value of 2 to the square root of 3 between two numbers. These numbers get, the more accurate I get, the closer and closer they get together. So eventually what happens is we reach, when we go to infinity, we reach a limit. Now, we're not really going to talk about limits that much in this class. It's a calculus subject. But I just want you to know that this has a meaning. It's just not real straightforward, like 2 to a fraction or 2 to an integer. Okay? That's just a little piece of extra information about evaluating exponential functions. That's it for today.
Yeah.
Dan, you have to write it out.